Good morning. All right, I'm gonna change this one a little bit from what we had originally written down. I added a fluorine here instead of a chlorine because it was only like 3 steps. So let's just review this fluorination pathway as well as just make it a little bit more complicated. So if it was a chlorine, we would have to add this acyl group first, add the MCPVA, or sorry, add the chlorine and then the MCPVA. So I'm going to go through a similar pathway to do this. There's actually 2 different ways we could do it. Now that I changed it, but let's do the acyl first. So throwing in AlCl3 and this acyl chloride. Oops. Too many carbons. This gives us a meta director. Before we would have added in Cl2, AlCl3, but because I'm doing this fluorine here, we're going to add in HNO3, H2SO4. From this point, it doesn't really matter if you do the MCPVA first or if you make the fluorine first. I'm going to add an MCPVA. This is going to insert an oxygen in between my ketone and my aromatic ring. And now I just have to go through that same pathway to make fluorine here. So if I add in zinc, mercury, HCl, I can make an amine. Throwing in NaNO2, NHCl is going to give me a diazonium. So N2 plus here. And the last step is HBF4. Someone asked me a question in the chat, and I'm going to look up the answer real quick. I can't remember. Yeah, okay. I think you do need to add in. Yeah, I don't think H2 and platinum actually works for reducing a nitro to amine here, so you have to use zinc HCl. Someone in the chat asked that. Okay, I'm going to start off with, I believe it's the fall exam 2, where we're going over aromatic versus anti-aromatic versus non-aromatic. We didn't really cover this planar concept, so don't really worry about that. So let's take a look at this first one here. So we have our 4n plus 2 rule. In order to have an aromatic compound, we either need to have 2, 6, 10, 14, 18, etc. electrons. For this one here, all these nitrogens already have double bonds attached to them, which means that all these lone pairs are going to be localized. And I can talk through that a little bit in a minute. So we are only going to worry about the double bonds for this. So this has 3 double bonds, which would give us a total of 6 pi electrons, which is going to be in our aromatic category. Okay, this next one here, there was a lot of questions in the 930 class on what's the difference between anti-aromatic and non-aromatic. Non-aromatic is literally not aromatic. So this here, these are both sp3 centers. You can't do resonance through them. There's no p orbital for these centers here. So these are not fully conjugated electrons around your ring. There's not like a cyclic system there. These electrons stop here. These electrons stop here. This is considered non-aromatic because it is literally not aromatic. Doesn't meet the fact that it's fully conjugated. Versus something like this bottom example here. This nitrogen, both these nitrogens don't have a double bond already attached to them, which means that their electrons can be in the pi orbitals. So we can count them for our aromaticity. So we're going to have 2 lone pairs as well as 2 double bonds, giving us a total of 8 pi electrons, making this anti-aromatic. We have one lone pair from this negative charge here. We have how many double bonds? 8 double bonds, giving us a total of 18 pi electrons, which is over in this aromatic group. This would be aromatic. This has a total of also 8 double bonds. There's no lone pairs, so this could give us 16 pi electrons and be anti-aromatic. All right, so how do I know whether or not to include a lone pair or not? I'm going to kind of go through that concept one more time. I like to use pyridine as an example. So this has a lone pair and a double bond to it. When you have a double bond, the electrons in the double bond are in your pi orbital, which means that these electrons here have to be in the opposite orbital. That is going to be perpendicular to the plane. 1, 2, 3, 4, 5. Okay, so if I draw in some orbitals, this nitrogen has a double bond to it. There's another double bond here, another double bond here. The lone pairs from your nitrogen have to be going in the orbital that's perpendicular to the plane, which means that those pairs can't be used in resonance, which is what makes them delocalized, or sorry, localized. Let's get these messed up. So there's already a double bond attached. Which makes this lone pair localized. We have the opposite. So no double bond on our nitrogen. We have a set of lone pairs. Now these can be in that orbital that is parallel to our pi plane. So these can participate in resonance. Which means that we're going to count them. That's a plus. The kind of pinnacle example of this is using for furan. So with oxygen, we have two sets of lone pairs. If we do a resonance, so if we push these electrons down, now we have a double bond to this oxygen. So we have the same concept we did up here, which means that these lone pairs would be localized. And that the other set of lone pairs were delocalized. So because of that, this is going to have one set of lone pairs that counts, two double bonds. This is going to have 6 pi electrons. Same thing up here, one set of double bonds that counts, two double bonds, 6 pi electrons. These pi electrons don't count, 3 double bonds, also 6 pi electrons. All these are going to be aromatic. And it just depends on whether or not you have a double bond currently attached to that heteroatom. Okay, so let's look at, what did I do next? I did this mini synthesis page. So I'm mostly going to go through the fall 2020 exam 3. I'm going to start with this page. So I'm giving you the number of boxes you need. If you have a 2-step reaction, like for instance, a Grignard, you add the Grignard and then you add water. Those are going to be considered 2 different boxes. So for this first one here, I need to add some sort of alkyl group. There's 2 different ways you could do this. You could either have the methyl through a Grignard or the isopropyl through a Grignard. I'm going to do it with a methyl through a Grignard. So if I add in chlorine, AlCl3, I didn't really give myself enough room in that box there, but I'm writing in Sharpie, so it's a little bigger. That would give me the majority of what I need. And then from here to get to our product, I just need to throw in a methyl Grignard. So it'll be 1 MEMG Br 2 H2O, and that can give us our final product. Okay, I'm gonna this one's a little long, I'm gonna work backwards through it. So in order to make this, I have to have a ketone. Oops, not aromatic, just the regular, don't draw on those double bonds. I'm coming from a chlorine, I probably wanted an alcohol, so I got to get from a chlorine to here, which should be somewhat straightforward. If I add in a small base, I can make this double bond here. I want my OH to probably be in the same spot as this chlorine was. So I got to add an anti-Markovnikov. So BH3 THF. NaOH and H2O2. These markers are all dying. Let's me replace that chlorine with an oxygen. From here, if I want to get to this, I can throw in PCC and then my amine. So that was a pretty long one. Let's take a look at this next one, which should be a little bit shorter. We're making a cyclic acetal. We throw in PCC, we can make a ketone. From here, we just need this diol, and we can make that product. Our next one is an order question. So these two are meta to each other, which means we need to add in, well, we're making an amine, we're making a Cl, so we probably want to add a nitro first before we make the amine. The nitro is gonna be a nice meta director. So if we add in HNO3, H2SO4, we can make our meta director. So from this point, throwing in our Cl2, AlCl3, gives us the chlorinated version of this nitro, and then we just need to reduce it to an amine. So zinc, mercury, HCl will let us reduce this down to an amine. Oh yeah, you could also do, someone asked in the chat if you could also do iron HCl. Yeah, that also works. Okay. I'm going to do the synthesis problems. So this was a bit of a tricky one for most people because it looks like you can just add in Cl2 and then add in Cl2 again. The problem is that if you add in Cl2, you have an orthopara director. So you could easily add your Cl here or add it here, but there's no way to get it to that meta position. So in order to get it meta, what you're going to have to do is go through the diazonium pathway. You can take a diazonium, add in copper chloride, and get a chlorine again. And that's going to be the easiest way to do this. So if we throw in something that's going to make this a meta director, so if we throw in HNO3, H2SO4, let's see, we can add an NO2. This is a meta director, and we can now throw in Cl2, AlCl3. We've got the structure we want for our final product. We just need to transform NO2 into a Cl. So from here, we need to make a diazonium. So either iron or zinc, mercury, HCl. Gives us our amine, NaNO2, HCl, kind of dying. gets us to a diazonium. It should just be N2 plus. From here, copper, chloride, Cu, Cl can get us to our final product. All right, this bottom one is actually a lot longer than I realized, and it's longer than anything you guys would see on your exam, but I'm gonna go through it anyways. We are going to flip an oxygen, which is gonna be pretty difficult. If I take a look at this, I have this ketone over here, this ketone over here. Nothing really happens to this side of the reaction, which means we're probably gonna wanna protect it so that we don't have to deal with it when we're doing a lot of reactions over here. So if we throw in our H plus, and let's do the 5-membered one. This diol, we can make our protected ketone here. And let's see, now we have to do a bunch of reactions in order to flip where our oxygen is. So we want to get rid of the oxygen that's here. So if we throw in LAH, we can reduce this down to just our alcohol. We could, so we want a ethyl group on here. So throwing in PCC. Followed by a Grignard to give us that ethyl. If we throw in PCC one more time, we almost make our final product. We just needed to insert an oxygen. So we have a secondary and a tertiary center. We throw in MCPBA. We'll be able to insert the oxygen there, and then H plus and water is going to let us take off this acetyl group here. Again, that was a pretty tough one. I mean, I would definitely say no that with this MCPBA, how this reaction works and where to insert the oxygens, but this I'd say was a pretty long one. This is what, 1, 2, 3, 4, 5, 6, 7 steps. And I think all your guys' ones can be done in 5. So that's a bit of a hard. What did I do there? Oh, it should say PCC. Oof. There we go. Hard mechanism. Not mechanism, synthesis. Okay, I'm gonna go over the mechanisms next because we haven't done these in a while on an exam. So let's take a look at these. Let's start with this enamine one first. So we have a secondary amine. First step of every reaction in chapter 19 starts the same way. We're going to pick up a proton. So picking up this proton gives us a positively charged carbonyl. Our amine can come in. Attack at our carbonyl to give us an OH and this positively charged amine here. We're going to do a little bit of a shuffle. So I'm going to lose the proton from my amine. We're going to re-pick it up on this oxygen. Our amine can then come down, kick out water, and make an amine. So these first couple of steps are going to happen in every single one of the mechanisms in chapter 19. You get a protonate, you have some sort of nucleophile attack. You're going to switch your proton from this, in this case, nitrogen, over to your oxygen. You're going to kick out of that oxygen, and then that's where those mechanisms start to change. So for the secondary amine, we've got a double bond, a positive charge on this nitrogen. This compound is going to want to be neutral. So in order to do so, it's going to pull off a proton from one of its two beta positions. The base that's in solution is the amine, which is very large. So it's going to be selective for your less substituted center. And this will let you form an enamine. So there are some questions in the 930 class about when do you form an enamine versus when do you form an amine. I'll put this back up in a second. Essentially, you're looking at versus if you have a primary versus a secondary amine. So if I have two reactions, with these two different amines here. So this secondary amine is going to form this enamine versus our primary one. Secondary. Will form this amine here, or enamine here. So looking at the two of them, This H is really easy to pull off. So if we wanted to make this neutral, we could just lose an H. To give us a stable imine here. So we don't have any negative charge or positive charges here. This one is now stable. Versus this over here, we have 2 bonds to carbon on either side. We're not going to break one of those off. So instead, we need to pull off one of these H's, which will allow us to get this enamine instead. So if you're starting with secondary, you're going to end up with an enamine. If you're starting with primary, you're going to end up with an amine. All right, I'm going to put this mechanism sheet back up. Don't worry about this resonance thing. We're not going to do that. So for a system like this, we didn't really talk about that this much in our or this semester, but the way that this works is if you have 2 different aromatic rings, you're just going to use the one that has the higher priority group on it. So we have a number 1 group for this OH, this O, ester here is going to be a group 2. On this ring, we have a group 5. So this ring has the group 1, that's the one we're going to use. We need to make an electrophile. So if we throw in, or sorry, we have these 2 compounds here. So let's combine them to make our electrophile. So we have HNO3 and H2SO4. You can pick up a proton. Sulfuric acid is the better acid, so that'll make H2NO3. Which is going to fall apart. We're going to have the electrons from this negatively charged oxygen take out the water and make N2. Which is a really electrophilic nitrogen. From here, you could draw the ortho or the para product. I don't know, 9 with 1. I'm going to draw the para. So I'm going to have my para position come in, do an attack. Ooh, I'm going to try to draw this over here. So let's go here. We are going to break our aromaticity. We get a positive charge on our carbon. We need to pull off this H here. So the base we made originally, which is HSO4 minus, can grab this proton. We'll re-aromatize. Should be para. And we can add this nitric group to our para position. You could also add an ortho, that would be fine also. So all these reactions are going to be very similar. You need to have your aromatic ring is going to attack an electrophile. You'll end up pulling off a proton, re-aromatizing, oops, to make a final compound here. And you'll have to make some sort of electrophile. So for this one, we're going to make this N2 here, or NO2 here, which can be attacked and easily added. All right, I'm going to go through some problems and then probably call it. So this little page I didn't talk about, which is here. Let's take a look at this. So first one is a chlorination. We've got Cl2, AlCl3. This is a group 1. This is a group 3. We're going to favor our group 1. Oxygen's really small, so we can either get the ortho or the para product for this one. So in general, if something is pretty small, like we have this OH here, we're adding in Cl2, AlCl3. This is going to end up adding to both ortho and para. We do something big, like instead of just a chlorine, we're adding in something that is like this acyl group here. This most likely will just give us the para product. So if I was asking you to draw this one, this would only have one product. Which would be this. So because it's such a large group, it's only going to add to the para position. And same thing if you have a large group already on there. So like, for instance, if I have a terp-butyl and I try to add in, let's say, Br2, FeBr3. So even though the Br is a small group, we already have a large group on there. So this is going to be your major product for this one also. So anytime you're dealing with a large group, it's going to add para. Unless it's a meta director, in which case it's will add meta. Okay, which is going to end up applying to one of these. I'm going to go over the addition or elimination addition one on this page because it's a little bit big. So the next problem was Br NaOH or NaNH2, sorry, NH3 and H3O plus here. So this is our benzyne. This is our triple bond to the benzene ring. Not going to go through the whole mechanism. You're originally going to make one of two benzynes. You're either going to make your triple bond here or end up making it here, which gives you 4 different positions you could potentially add to. For this one, you could add to the ortho or the meta position. And then for the second one, you could add to the meta or the para position. So we have 2 metas. If you want to think of this as like a random occurrence, 25% of the time, you'll add to this ortho, 25%, you'll add to this meta, 25%, you'll add to this meta, 25% you'll add to the para. We have 2 that are the same, which means of the 3 products we could actually make, only one of them is going to be our major, which would be this one. Because this, when you add the NH here, it only happens 25%. When you add it para, it only adds 25%. So the fact that you add meta twice is going to make this your major product. All right, the rest of these are pretty straightforward. Except for one of them, I think I wrote the wrong reagents on. Or I actually taught it in this class. I'm gonna cross this one out and do something different there. Okay, so for this one here, we have an oxygen and a sulfur on it. Doesn't really matter which one you put the oxygen and the sulfur on, because this could potentially be a wedge to an or sulfur, a wedge to an oxygen. This is actually the same thing as these two are the exact same answer. They're just like a plus minus version of it. So as long as you make some sort of form of this cyclic acetal, that'll be fine. We have a secondary amine. We have two secondary centers, which means we're probably going to form two different products. We could either make the amine where the double bond is on the left, or enamine where the double, oh wait, that's not right. I draw it up here. Enamine where the double bond is on the left, or the enamine where the double bond is on the right. Both of which would be correct in this example. All right, so we are adding, we have this dichlorinated compound. We have a terp-butyl, so this is going to add para. And now we are in solution with more of this because I added two equivalents of it. So another one of these can interact with this chlorine over here, and we can dialkylate this. To give this product. Next one is a Wittig reaction. So we're just kind of doing combining our two double bonds together. So breaking here, merging them together. MCPBA favors phenyl groups over secondary positions. So we should insert the oxygen. Space. Here, I'm guessing this was supposed to be KCN, HCN here, which would let us do an attack on our ketone here, giving us an alcohol and a nitrile. This is a reaction we learned later on. I'm not sure why that was on there. This one is a primary amine, so we can just make an enamine. And the last one, we have a meta director and this acyl group here. So we're able to add the acyl group. Meta. Okay, so for your actual, I was going through and studying these from exam, practice exam 2. Do pages 2 and 3. So that's the aromatic versus anti-aromatic. And then page 3 is the NMRs for aromatic compounds. We switched them this time. And then for exam 3, maybe pages 4 onward. So we're not doing that page. The first page is the nomenclature and functional groups. We're going to be doing the stuff from exam 3, and then everything else is from exam 4. Okay, that is all I have for you guys. if you guys don't have any other questions, I will see you guys on Wednesday. There is a question in the chat. Yeah, someone wanted me to go over if I have a CL and I add in, what is it, NaOH at 70 degrees. H3O plus here. So typically this doesn't work. This here would give you no reaction. You probably can't see my writing again. Your book talks about a way to do it at like 350 degrees. This is an example of something you probably don't want to do because it's going to most likely explode. So at extreme temperature, you could technically get this to work. But the easier way to do it is if you have a nitro group that is either ortho or para. So NaOH. Oh no, she's dying. I think that works. This is going to be able to do this reaction at a normal temperature to do that transformation. So your book talks about this metal reaction, but this is really one because this is just super dangerous. How do you know when to add O to the ring itself when doing the MCPBA reaction? You know when to add O. So like, this concept? So for this, you're just following your like MCPBA reactivity. So it's most reactive if it's just H followed by a tertiary position, followed by a phenyl position, secondary, primary. So here I have a primary and a phenyl group. So it's going to insert itself in between the phenyl and between the ring and the carbonyl here. Yes, this is 350 degrees. Sarah, you might have to send me an email because I'm not exactly sure what you're talking about if that wasn't it. Any other questions? Okay, if not, I will see you guys on Wednesday.